Thanks a lot to the organizers for inviting me, and thank you all for coming. So this work is joint work with a lot of people who, all of us were at Michigan when the work was done, but now I am the only fixed point. Jake has moved to Georgia Tech. Chansu, a PhD student whom Jake and I co-advised, he's moving to Google, Pittsburgh. Zifan was an undergraduate when he did this work and has moved to Yale pursuing his PhD. And Audra is now a postdoc at Boston. So what is this talk about? So the talk is actually about this pipeline. So in a lot of machine learning and statistics applications, what people do is they start with the data. You inject some controlled amounts of randomness to get some perturbed data, and then you run some optimization algorithm to finally get your prediction function for a regression problem or a classification problem or a structured prediction problem. And the question we really wanted to answer, which I don't think we've fully answered, but we've made some progress, is how do we show in some principled way that this randomness is acting as a regularizer? Right, so that was kind of the overarch, the framework is, can we understand addition of structured randomness as a regularization?
Do you have a short intuitive explanation of what regularizer?
Yeah, this is just very, very big picture. I'll zoom in, yes. I'll also say why somebody doing real-time decision making might be interested in this. So I'll come down to to more details. But this is just to sort of set up the higher level intuition. So some of you might know about this technique called bootstrapping. It's very, very widely used in statistics, also in machine learning. And maybe the most well-known incarnation of this is random forests. Right? So the idea behind random forests is you have some data, you subsample the data, you do this many, many times in parallel, and on each subsample you train a decision tree, and then in the end you maybe average these decision trees to get a forest. Right? And random forests are one of the best sort of off-the-shelf predictors. So this idea is used a lot. And here the controlled amount of randomness is in generating these bootstrap samples. So we use randomness to select subsamples from the samples we have. And this seems to work very well in supervised learning. Another procedure of this sort is the dropout, used very widely in training neural networks. And there, it's sort of related to this idea of a blank out noise, which is if you have most of the time we represent our data using some features, right? So let's say you're doing credit card scoring, and you might have features like how much of what's the annual income, what's the zip code, what's the amount of current loan the person has. So you have all these features, and you might try to add some structured noise to the features before feeding the raw data to your machine learning algorithm. And one of the noise they use is for any feature you keep it with probability p, otherwise you zero it out. So it produces sort of sparse matrices that in expectation are equal to the initial feature matrix that you saw. So these are just examples to tell you that this happens all across the board. This type of pipeline, which is central to what we study, is all over the place. And it's not just us, but many machine learning researchers have tried to understand what's going on in these types of algorithms. And as I said before, one of the emerging viewpoints is that, well, really you can interpret addition of this randomness as regularization. Now, there was a question about what is regularization for those of you who don't necessarily have machine learning as their primary research area. So regularization in general, it's a ill-defined term, but it usually means something you do to control overfitting in your model, right? So what is overfitting? Overfitting is if you use a very complex model and you have limited amounts of data, then it might just memorize, right? So, and it will not work well out of samples. So it will work very well on the data you feed it, but it's not going to generalize very well to out of sample data. And if that happens, people say, oh, my model has overfit, and then you have to do something. What you do is regularization, right? So that's kind of a vague definition. So what we want to say is somehow that this perturbation is acting as a regularizer. It's preventing overfitting. And there is a nice book now that includes contributions from lots of researchers. There were a series of NIPS workshops during the years 2012 to 2014, and this book sort of evolved out of the contributions presented there. So if you're interested in this general area, I recommend this book titled Perturbations, Optimization, and Statistics. OK, so lots of high-level intuition. Let me get down to some concrete examples. So here's actually maybe the most basic result in this area. And like a lot of basic results, this has been rediscovered in different communities. And it goes by this name of the Gumbel lemma. And I actually, until a couple of years ago when I started research in this area, I didn't know about this. It's a very basic result. And here's what it says. So suppose you have n numbers, theta 1 through theta n, right? And what you want to do is you want to draw an integer from this set 1 through n at random. And you want the probability that you pick integer I to be proportional to e to the power minus theta I. Okay? And there are many, many situations where you want to do that. Maybe this theta I is some kind of an energy from a graphical model, and you want to have a probability distribution whose probability is proportional to e to the power minus this energy term. Right? So these types of Gibbs-like distributions arise all over the place. So it's not too crazy for me to ask that I want to draw from this distribution. And in practical scenarios, n is very, very large. But if here, think of n as some fixed small number, just to understand the result. OK, so far the Gumbel distribution is not here, but let's bring it in. So the Gumbel distribution is a distribution with this density. And it is min stable. What does min stable mean? It means that if you draw independent draws from this distribution, and you take the minimum, that is still a Gumbel. So it's stable under taking minimums. And there is a version of this which is max stable. So Gumbels come in two forms, min stable and max stable. So this is the min stable version. And what's the connection of this distribution to our original problem? It's very interesting. So it is this perturb and optimize pipeline that kind of connects to two things. So suppose I take my original theta i's. So remember, I have these n numbers, and I want to generate distributions such that the probability is proportional to this. What I can do is I can add independent Gumbels to each component, and then just take the minimum after adding the perturbation. Okay? And then the probability is just the correct one. So the probability that you will select a particular integer I0 from this set after adding this random perturbation and minimizing is exactly what you want. Okay, so it's surprising that this is true. So there's something more general lurking underneath. So this result actually is kind of known in social choice theory. It's known in economics. People who do graphical model inference use versions of these to approximate Bayesian inference, and then it also shows up in online learning, as I will discuss more later. So how many of you have seen this result or similar result before? A couple of hands. Okay. Oh, hi.
So Z is can take positive and negative values, or it's only positive?
This is on the positive real line. Any constant shift will not alter the result because the argmin is insensitive to shiftings. And then there is a corresponding version for max. So if you draw from not the min stable Gumbel, but its max stable cousin, then you can also get the argmax version of the theorem. So far, things are making sense. Stop me anytime if I stop making sense. OK, so online learning. So this is a workshop on real-time decision making. We've seen already online learning come up in several talks, and it will also show up in later talks. Vijay, in his a very nice talk on Monday was talking about online algorithms for matching. So within computer science, there are two communities who look at online algorithms. There are people in machine learning like me who look at online learning algorithms. And we usually look at regret. And the state of the algorithm is usually something simple. It's maybe a weight vector that we are learning. And then there are algorithms researchers who look at online algorithms for solving combinatorial optimization problems, maybe online matching, online shortest paths. And there, the algorithm usually has a richer state, internal state, and people look at comparative ratio. So there are differences, but the two communities have a lot of things in common. So I'm approaching online learning more from a machine learning point of view. And these online learning algorithms, as the name suggests, they work in this scenario where you have data coming at the algorithm in a sequential incremental fashion, and you want to do some efficient computation each time more new data arrives. And that's kind of almost by definition of the setup well suited to real-time incremental streaming applications. So let's try and talk. I'll spend the majority of my talk time talking about perturbations in online learning. Okay, so far I was just talking about perturbations in general, but now I want to talk about perturbations in online learning. So let me just introduce to you this extremely basic problem in online learning. So people who are experts will find this extremely boring, but this is just so that everyone is on the same page. So suppose you have, this is the famous experts problem. So time goes on in discrete steps, 1 through t. At every time step, the learner has to select, maybe there are n experts, each giving the learner some advice about how to behave. And at every time, the learner's job is to pick one of the experts, one of the sources of advice. Now, these experts could be real experts, maybe humans, or computational models, maybe weather models, maybe this is a weather prediction task, or they might just be statistical models, right? So this problem doesn't care about the nature of the entities generating these predictions. It's pretty abstract. So I choose an integer I'm the learner, I choose an integer from 1 to n, and then nature reveals some outcome which sets n losses. So every expert at every round suffers some loss. And we assume that loss is bounded, and we've scaled it so that it's in the interval 0 to 1. So after choosing one of the experts, I get to know the losses of all of the n experts. Okay, so if I went with an expert that had high loss, well, that's a bad day for me because I should have gone with someone else who had a smaller loss. So I suffer the loss. So LT is a vector. So every time t, I see a vector. After I make my move, I'm the learner. I see a vector with n numbers in it, and I suffer one of those numbers, namely the numbers corresponding to the index that I picked. And this happens again and again. And it's typical. This is not the only measure of success in this setting, but this is a very widely used measure of how good the algorithm is doing. So we will add up our losses. So LT, IT, remember that number is what I suffer instantaneously at any given time. And then I subtract from that the minimum loss in hindsight. So suppose this game is over. After t rounds, I can compute the cumulative loss for each expert. For each fixed I, let's say I is 1, I can just add up the losses of the first expert. That's going to be some number. Then I can add up the losses of the second expert. And I do it n times, and I say, which is minimum? So if I knew the losses in advance, I could have just stuck to one of those experts and attained this loss. Maybe I did worse. I'll just measure this difference. And I'll take the maximum over all n's, maximum of this different over all n's, which because of this minus becomes a minimum here. And I call this my regret. This is the learner's regret, how bad they feel when they look back. So is the protocol and this definition clear? How many of you have already seen regret defined like this? So that's almost everyone. So good. That's really good. So a little bit of history. So I teach at Michigan, and there's Michigan State University about 1 hour north from Ann Arbor. And Jim Hannon, who was a statistician in the stats department, he proved one of the earliest results in this area of online learning using regret as a measure of success. And so now, if someone designs an algorithm whose regret grows sublinearly, Now, why is sublinear important? Because, see, losses here are scaled, right? So this quantity, anyways, trivially, doesn't grow any faster than linear in t, right? At max, I can suffer constant regret. So if you design an algorithm that has regret some constant times t, that's not a very good algorithm. So I want this regret. Ideally, well, maybe this can be constant. That would be great. But at least it should not grow as fast as t. So because of Hannon's seminal contributions, now we say an algorithm is Hannon consistent if its regret is small of t. Okay, and then there are versions. I mean, you have to be you have to have regret in high probability if your algorithm is randomized. And the reason this is a screenshot of his paper called Approximation to Bayes' Risk in Repeated Play, published back in the 1950s. The reason I put this screenshot here is I don't think you can read it, but the underlying part of this paper says that what he's doing is that he's adding randomness. Okay, so this idea of you look at the losses that have occurred in the past, well, that's all you got. If you're the learner, you don't know what's coming in the future. All you have are losses from the past. What he said is, look at the losses in the past. Don't follow the person who looks best currently, because who knows, maybe in the future they're bad. But add some random perturbations. And then choose the best after perturbing the losses. So that's the part I've underlined. Just to show that this idea was back, even in the first paper, this idea was right there. So let me say more. So it might be tempting to design algorithms that simply minimize the past losses, right? So I am at time t. I know for every expert, I know their losses in the past. So I'll just add them up and pick the one that has the minimal loss. That seems like at least a reasonable starting point. And this is called fictitious play in the game theory world, and it's called follow the leader in machine learning. It works well, but only under very sort of you have to put a lot of assumptions. In general, it doesn't work. It doesn't even work for this 2 experts case. So here are 2 experts. Here are the losses. Of course, the learner doesn't know that these losses are coming. On day 1, we don't know what they do. Maybe they just randomize. But after day 1, having seen this column, and if that's your strategy, you're going to pick the second expert at day 2, right? Because you're going to say, well, this expert got loss half. This expert hasn't suffered any loss, so I should go with the second expert. So you go with them, and then the reality flips. Nature says, well, this is bad, this is good. And now you follow this one, because the cumulative loss after 2 days is 0.5 here and 1 here. And then nature flips again, and nature again, it keeps doing this alternation, and you suffer really bad regret. Why do you suffer bad regret? Because the best expert in hindsight is only suffering constant loss every other round, right? So it's suffering loss 1 every other round. So the loss of the best expert is growing as t over 2. But you're suffering a loss every round. So your loss is t. And the difference of t and t over 2 is t over 2. So your regret is increasing linearly. So it's an unstable algorithm. It's a deterministic algorithm. So an adversarial nature here is being adversarial, and it's able to take advantage of this instability, that it's very predictable. You're deterministic, so you're predictable. So it can generate these types of losses and cause high regret. So Hannon's idea was to stabilize this algorithm. It's very unstable by its nature. So let's stabilize it. And let's stabilize it in a very peculiar way. Let's stabilize it by adding randomness. And this family of algorithms where instead of following the leader, you add randomness. And it's called follow the perturbed leader, machine learning. And in the game theory literature, it's called stochastic fictitious play. But both names convey the same underlying idea, that it's basically doing the obvious thing, the naive thing, which is, well, just go by past performance, but just smooth it out a little bit. And eta here is a trade-off parameter. If eta is too small, then you're adding a lot of randomness, and you're not paying attention to the past performance, which seems weird. You should pay attention to past performance. And if eta is, the other extreme is when eta is very large, then you're back in this deterministic world where you're just going completely according to past performance. And Hannon's original choice was he was choosing these ZIs independent across all n experts from the uniform distribution over 0, 1. So in Hannon's original 1956 algorithm, these were just uniform random variables. What's interesting is that this is maybe if uniform is like maybe the first continuous distribution that comes to your mind. Oh, question?
Sorry, do you choose the zi's once, or do you choose them randomly each time?
Yeah, so that's a good question. Do you choose them once, or do you choose them again and again? It depends on what is your assumption on the adversary. If the adversary is oblivious, just chooses the loss sequence ahead of the game, then you can just choose them once. But if the adversary is adaptive, you have to protect yourself against them realizing what kind of underlying randomness you're using and exploiting that. Then you have to draw fresh randomness. Any other questions about this? Yes?
I haven't said it yet, but what information do you need to tune eta? You said.
Yeah, so typically, this eta ends up being at the scale of square root of t.
I know, but
yeah,
in deriving that optimal square root t,
yeah,
what information are you using?
Oh, like what information about the game is needed? So actually very minimal. So once you assume that you have bounded losses and you know the bound, that's pretty much everything. The way I've written it, it seems like you need to know how long the game will last. But you can also have a time-dependent eta. So not eta, but eta sub t. And it usually doesn't matter whether you use, at least in the simple problem, it doesn't matter whether you know the time horizon upfront or you slowly decay eta as a function of t. So it's not a lot of information. And I will talk about, if I have time, I will talk about an algorithm that is parameter free. So this one has a parameter. And in practice, you don't want algorithms with tuning parameters, because who sets them, right? But there are versions that are tuning parameter free. Any other questions about? Okay, great. Okay, so there is a choice for eta, which actually gives the correct scaling. In this simple problem, it gives you a scaling of square root t for the regret, which is optimal. No algorithm can do better than that. However, choosing this simple distribution, which is just uniform, does not give you the right dependence on the number of experts. So you get the right dependence on the time, but you don't get the right dependence on the number of experts. Yes?
Just to understand the parsing, the zi over eta, that's outside of the sum or inside the sum? Because this is
oh yeah, my scope is not clear, right? So this is just the sum of the losses, and then I'm adding just one random number. Yes. So this sum ends here. Now there are follow the perturb leader algorithms where you move the zi inside and then it is a zi s comma I. So there's actually a very nice paper called Prediction Using Random Walk Perturbations, where actually that's one of the ways to get rid of this tuning parameter, because you add a random walk and the random walk inherently scales as square root t. So actually there is an algorithm where you add inside the sum. But this is Hannon's original algorithm. He didn't do it. Okay, so this algorithm, this is an algorithm family because we can choose different ZIs. One particular member of that family, already discovered in the 50s, gives the right scaling in t, so that's great. But it doesn't give the right scaling in the number of experts. It gives polynomial dependence on n, while in fact the minimax optimal is logarithmic. So how do we get the right dependence? And we get it through this very, very famous algorithm, which again, I think almost all of you have probably heard about it under different names, multiplicative weights or exponential weights. The basic idea is extremely simple. You initialize some weights. Maybe you set them to one weight for every expert, and initially you don't know how good they are. So you just set them to 1. And at every round, what you'll do is you'll use these weights to draw, you'll select one of the experts at random using those weights. You'll select them with probability proportional to the weight. So you want to keep these weights non-negative because you'll interpret them as unnormalized probabilities. And this is how you will update your weights. So if an expert doesn't do very well, you incur a lot of loss, then you downweight them. So you say the weight goes down, e to the power minus some tuning parameter eta times their loss. And if they don't get any loss, if loss is 0, then you keep the weight as it is. Right? So this is the famous multiplicative weights or exponential weights algorithm. And this algorithm achieves optimal regret for this problem. So square root t and then square root log n That's its dependence on time and number of experts. So this is optimal. Now, how is this connected to Hannon's algorithm? It just seems like a different algorithm. So the interesting thing, and again, experts in the field know this, so I'm probably boring them. But if you don't know this, it's a very interesting thing to note that through this Gumbel lemma that I showed you earlier, you can reinterpret this algorithm as a follow the perturb algorithm where your perturbations are not uniform, but they are Gumbel. So that's a key thing to remember from this talk. This is a folklore result in machine learning, but it's not widely known outside of it. So recall that FTPL had this form. And it turns out, this is the sort of the main point of this slide and the first part of the talk. And if you remember one thing from the talk, just remember this. That exponential weights is actually, it's an FTPL algorithm. It's a perturbation-based algorithm, provided you choose your perturbations from the Gumbel distribution. And this just follows from the Gumbel lemma. So Gumbel lemma said that if you have some numbers and you add Gumbel perturbations, then the probability that you will draw the ith number is proportional to e to the power minus that number, right? That's what Gumbel lemma said. So move this eta over to here, because the argmin doesn't change under scalings, under positive scalings. So this whole thing is, I'm taking the argmin of eta scaled sum of the past losses plus zi. And if zi is the Gumbel distribution, then I know that the probability I will pick a particular expert I is going to be proportional to e to the minus this thing, right? So e to the minus eta sum of past losses. That's going to be the weighting, right? And that's what this algorithm is doing, because the weight at time t is going to be proportional to e to the power minus eta sum of the losses in the past, because you multiply with an exp, so these accumulate additively inside the exp. Yes.
That means whether you perturb in the beginning or anytime during the process, it's stochastically identical.
If the distribution will be the same. Yes. So exponential weights or multiplicative weights can be reinterpreted. It's the same algorithm, but you're just reinterpreting it as an FTPL algorithm. But what's interesting is you can also view exponential weights as follow the regularized leader algorithm. Yes?
Sorry, on the previous slide,
yes.
Doesn't this say that the algorithm is optimal whatever eta is? Because...
No, if eta is too small or too big, you're going to get a bad algorithm. So eta has to be tuned properly.
So on the previous slide?
On the previous slide, yes.
When you
so there's this eta right here.
The bottom bullet point.
Oh, yeah, I should have added here with the right tuning of eta.
Okay.
Yeah, I'm not claiming. Yeah, so this might seem I'm claiming it's always optimal. No, with the correctly tuned eta. Yeah, the eta has to be tuned in both algorithms. Well, it's the same algorithm, actually, so it has to be tuned. Okay, so I showed you this exponential weights algorithm, and fact number 1, it can be interpreted as FTPL with Gumbel distributions. Now fact number 2, and this is more well known than the other one, the fact that multiplicative weights or exponential weights is basically using entropy as the regularizer. Okay, what does it mean? Technically, it means the following: that the probability vector that you put on the experts using which you draw them, you draw the experts, can be obtained as the solution of this optimization problem. So this optimization variable p, it's ranging over all probability vectors of length n. If I did not have this regularizer, then if I just minimize the inner product of a probability vector with a given vector, obviously it is in my best interest to put all the mass on the least entry, right? What do I gain by distributing mass? I don't get anything. So if I don't have this, which is like eta is infinity, so then you don't have this, then this is just follow the leader, right? This part would just give you follow the leader argument. Even though you're doing probabilities, it will actually be deterministic. But if you encourage some entropy, you say, okay, no, I want to pay attention to the past losses, but I also want to have some kind of entropy inducing behavior in my optimization problem. I can explicitly add negative entropy as a term. So entropy is maximized for like completely uniform distribution, which means that negative entropy is minimized, right? So this will encourage the solution to go towards the uniform distribution, while this will try and make it deterministic. So then you do the trade-off using eta as the trading off parameter. And this algorithm, with this choice for the regularizer. Now this is called the regularizer in machine learning. So we think of this as the data part. This is what we see from nature. And this is what the designer adds. And I'm adding it so that my algorithm becomes stable and doesn't overfit too much to what has happened. So that's why I'm calling this the regularizer. And this family of algorithms is called follow the regularized leader. Just like we have follow the perturb leader, we have follow the regularized leader. And so if you use entropy, you get exactly exponential weights.
Okay, so
Yes.
entropy and sample from.
So here this solution directly gives you the probability distribution. So then you sample from it, yes.
It's Thompson sampling with something like Thompson sampling with this.
Yeah, I mean Thompson sampling usually it's implicit, right? You just draw from the posterior, but here I'm explicitly giving you. Here's the vector, draw it from. Yeah. Okay, so I have what, five more minutes?
I'm supposed to know that, aren't I?
What is that?
I think you have a bit more.
Yeah.
You stopped. You were delayed a bit. So.
Okay, so maybe I can go on for another few minutes. Okay, yeah. Okay, so actually this part is ending. So far I have not told you any new work. I've only told you common knowledge in the online learning area. But this slide somehow this slide and the following couple of slides summarize what we discovered in a series in 2 papers written over the past 2-3 years. So we know this, but we have this data point, right, in our space of knowledge about algorithms. We know that FTPL with Gumbel is exactly the same as FTRL with negative entropy. That we know. So okay, obvious theoretical question is there something deeper going on, right? Is this just an isolated fact, or is there some very generic connection? In particular, you can ask things like, okay, if I have a particular FTPL algorithm which is using some perturbations, maybe, I don't know, Gaussian or normal or Gumbel, can I always find a regularizer so that I have this equivalence, right? And vice versa. If you give me a regularizer, then can I always find a perturbation which is formally equivalent to it? And the answers are a mix of surprise and not so surprising, maybe. So yes, the connection between both of these algorithms they can be understood as different ways of smoothing a non-smooth function, and this will become clearer in a couple of slides. So that's kind of the high-level answer to the first question. The answer to the second type of question is yes. In this experts problem, and more generally in online linear optimization problems, you can always find an equivalent regularizer. So if you start from a perturbation, you can always find a regularizer, and you just use standard convex duality or Fenchel duality. So that's a nice direction. Interestingly, it doesn't work the other way around. So it's not the case that in fact, there are counterexamples. So there are regularizers for which you can prove that there is no perturbation which will make the perturb algorithm exactly equivalent to the regularized algorithm. But I would not say that the question is fully settled here, because in some sense, asking for exact equivalence is a little bit too much, because who cares, right? Maybe the distribution is a little bit different. As long as the overall learning guarantee, as long as the overall regret guarantee is still maybe within constant factors, it should be okay, right? So that a more general version of this question is still open, which is, if I give you a regularized algorithm for some online learning algorithm, and let's say it's minimax optimal or it has a particular regret rate, can I always design a perturbation which gives me the same learning guarantee? It maybe doesn't match the algorithm point-wise in terms of its distribution, but has the overall same guarantee. So that's still open. But at least you can't get an exact equivalent always. So let me just spend just 1 or 2 minutes explaining to you what I meant by, you can think of these two as smoothings of non-smooth functions, and then I'll open for questions and stop there. Okay, so here's a non-smooth function. So you have this is a function over vector. So G is a vector with n components, and this is just the pointwise maximum. So what's the maximum entry in this vector? And this is the function that is beneath the expert's problem. I've just converted my mins to max so that I get a convex function. Otherwise, I would have a concave function, and I want to use convex analysis. So this is the unsmooth function. This is the reason why in that counterexample the algorithm is flipping, because this function is non-smooth. Now this maximum coordinate function can also be written as the maximum over all probability distributions, simply because the maximum will be achieved at a basis vector. And what you do is when you add a regularizer, and now the sign is minus because of my max min swap. So don't get confused by the sign flip. But the point is, this is some non-smooth function of g. If I add a nice function like entropy, then it becomes smooth, because after this transformation, this new function actually has derivatives. Okay, so this function does not have derivatives. Anytime g has two entries that are equal, then the derivative is not well defined. It still has a subdifferential because it's a convex function, but it's not differentiable. So this thing makes it smooth. And this is a very standard type of smoothing in convex analysis. It's called inf-conv smoothing. You take the infemal convolution with a strongly or strictly convex function, and you smooth your function. So this is one type of smoothing. But maybe this is not this type of smoothing outside. If you don't know a lot of convex analysis, you may not think of this smoothing. Maybe the more natural smoothing is the standard integral convolution smoothing, where you integrate your function against a Gaussian density or something, right? So normal, regular, like Gaussian blurring for people who do image analysis. And so you could start from the same function, but you could smooth it this way, right? You could say that for every coordinate, I will add some randomness, and then I'll take the expectation. This expectation is under the randomness in Z. So this function hopefully smooths out the kinks in the underlying phi, because you're convolving with some nice distribution that has a density. And so this is the integral convolution smoothing. And the previous one is infemal convolution smoothing. So that's nice. So FTRL and FTPL are both smoothing, but they're smoothing in different ways. And the fact that if you have a smoothing of this form, you can always find a regularizer is just duality. So this is some smooth function. So you can always look at its Fenchel conjugate, and its conjugate is going to be a strictly convex function. So just almost for free from convex analysis, there will always exist a strictly convex function such that this smoothing can also be written like this, which is what we call the FTRL type of smoothing. So the point is, okay, this might not be easy to compute, but it will always exist. So for every perturbation, there exists a strictly convex function such that the FTRL algorithm with that function is the same as the FTPL algorithm. Now I cheated a little bit because playing the gradients of this function is the same as running follow the leader, because you just go after the person who has the maximum gain in the gain setting or minimum loss in the loss setting. In this case, playing the gradient would mean playing the gradient of this expectation. So the gradient is outside the expectation. But that's not what FTPL does. FTPL adds randomness and immediately optimizes, which means that gradient operation is occurring inside the expectation. But in linear optimization problems, expectation commutes with linear functions. In expectation, it's all OK. But for nonlinear problems, there is an extra step. You can't just talk about these smoothings and immediately talk about regret, because for nonlinear functions, you won't have the linearity of expectation, the expectation commuting with linear functions. So actually, that's it. I had other stuff, but it's more technical, and I think I've made the high-level point, and I'm also running out of time. So I'll just stop by saying thank you, and if you're interested, here are the papers on which this talk is based. And this is mostly the part I covered.
Thank you. Maybe one question, and we'll take the others offline. Yes.
So for the last point that you just made, so is it really that the smoothing is equivalent to online dual averaging? Is that what's going on?
Smoothing is...
Sorry, not the smoothing. Adding the random perturbation is actually equivalent to online dual averaging. That's the point about the nonlinearity that you made at the end?
No, the point about nonlinearity I was making was okay. So I'll have to say two things. So one is that yes. So in optimization also people understand this. So usually you want to smooth by adding an explicit function, right? Nesterov smoothing, right? You hunt for a nice function to add, so that after adding and doing the min and max, I get a nice smooth function. But you can also perturb. So there's a very nice paper on semi-definite optimization where this, like if you're optimizing like the largest eigenvalue of a matrix valued parameter, then instead of smoothing it explicitly, maybe you can just add a little bit of randomness and have a randomized objective, run an algorithm there, and then give bounds on the original problem by saying that I added only a controlled amount of randomness. The point about linearity I was making was more of a technical rather than a conceptual point. Simply, and maybe I didn't have time, so maybe I confused everyone. The point I was making was that the algorithm I described originally as FTPL is not the algorithm that plays the gradients of this function. It actually plays the gradient of the function inside. And so there is this issue of, is the differentiation happening before the expectation is taken or after? And I was simply saying that if your objective is linear, it doesn't matter. In expectation, it doesn't matter. So that was more of just a technical point, not a high-level conceptual point. Oh, and I should maybe say one last thing is, why should anyone care about perturbations, especially if perturbations always have a regularizer? It's because of efficiency. So I didn't say that. But FTPL algorithms were discovered for this reason, is that in a lot of online problems, like online shortest path, it's very easy to run FTPL because the oracle you need is simply the shortest path oracle. You're just adding random numbers to the edges and then feeding it to your standard algorithm. But if you add a regularizer, then the nature of your optimization problem changes and you have to feed it to a different solver.
Well, thank you for an elegant lecture.